All right, Chapter 1, Section 1. A lot of these things in the first chapter are going to be reviews from Algebra 1. We'll take our time to go through and make sure you understand and remember all the things that you learned in Algebra 1. So the first thing we're going to do is talk about sets of real numbers. And we're going to try to classify real numbers by the subsets that they belong to. So the first thing we want to do is talk about a set of numbers, or a set of anything really, and how we can divide it into subsets. Here we have a set of chess pieces, and the chess pieces make up a set. When we take this set, though, we can split it up into smaller subsets, still part of the overall set, but we can divide them and further classify them into smaller groups that we can call subsets. We can put the king in a subset by itself, the queen over here in a subset. We've got a subset of rooks, a subset of knights. We have a subset of bishops. And then finally we have a subset of pawns. Now each of these subsets, when we put them together, make up a chess set. If I talked about a chess set, I could be talking about any one of these elements. But if I talked about the subset of rooks, I would only be talking about these two elements here. And if I talked about the subset of queens, I would only be talking about this subset here. Well, it turns out we can break down the set of real numbers excuse me, in a very similar way. Real numbers, it's all the numbers that you're currently familiar with. There will be non-real numbers that we'll discuss later on in the year. For now, we're going to stick with all the numbers you know. The ones, the zeros, the 100s, the -3s, the 5.8s, the pi's. All these numbers that we've used in mathematics up to this point have been real numbers. So if I look at this set of real numbers, it captures all of those things that I just mentioned. Any number that you can think of is inside the set of real numbers. And the first subset distinction we're going to make as we go from real numbers down, we're going to break it down into two different subsets. One subset is rational. The other subset is irrational. Now we talk about irrational numbers versus rational numbers. If we look at the root word in rational, it's ratio. Rational numbers can be represented as a ratio of two numbers, or in other words, we could write them as a fraction. So in the rational numbers, we have things like 1. We could write 1 as a fraction, 1 divided by 1. We have numbers like 3. Well, 3 divided by 1 or 6 divided by 2, all those are rational. It's still fractions. We also have things like 0.25. That's a decimal, but we could write this decimal as a fraction. You guys are all fairly familiar with what 0.25 is as a fraction, I hope. It's 1 over 4. Other things we could write as a fraction. Let's talk about 0.33 repeating. Well, this seems to go on forever. It's a long decimal, but we could still write this as a fraction. 1 over 3. So anything we could write as a fraction is a rational number. It is a subset of real numbers. And we can use a letter to shorten and use as a symbol to identify rational numbers. We look at rational numbers, we can write them as a fraction or a quotient. So we use Q to represent rational numbers. Now let's come over here and look at the irrational side of this. Here is a subset of rational numbers, and then here is a subset called irrational numbers. Well, an irrational number includes things like pi. There's another number that's similar to pi called e. And anytime we take the square root of a non-perfect square, like the square root of 2, it's going to be an irrational number. The square root of 3, that's an irrational number. I'm not really giving you too much of a definition though right now when we're talking about irrational numbers, so let's clarify just a little bit. An irrational number is a non-terminating, non-repeating number. So an irrational number goes on forever. and it never repeats itself. Now, we're talking about non-terminating, non-repeating decimals here, folks. If I look at pi, we know that it approximately equals 3.14159, but it goes on forever. It never stops, and there's never a repeating decimal in there. E, Euler's number, it's another constant, kind of like pi, and it goes on in decimals, and it never stops. If you take the square root of 2 on your calculator, you're going to see a value pop up, but that value is an approximation. The square root of 2 is irrational. It has a decimal that never ends, and it never repeats. It goes on forever, and it never repeats itself. So you may be asking yourself, well, wait a minute. If an irrational number never ends, what about 0.33 repeating? It never ends, right? It never ends, it goes on forever, but it repeats. The 3 repeats over and over again, so 1 over 3 is in fact a rational number because it is repeating. So we have to have both these stipulations true. Non-terminating, non-repeating makes it an irrational number. And there is no symbol for irrational. We're just going to write out the word in total, irrational number. Now an important note here again is that any non-perfect square is an irrational number. So square root of 2, square root of 3. What about the square root of 4? Well, the square root of 4 is 2. And 2 can be represented as a fraction, so it's not irrational. But the square root of 5, not a perfect square, that would be an irrational number as well. All right, so underneath irrational numbers, we don't break it down into any more subsets. But here, we could take the rational number. It's a real number, and it's also a rational number, and it includes all of these values here, anything that can be written as a fraction, so we have decimals included here. If we get rid of the decimals, let's say we only want to talk about rational numbers that have no decimals. So like 1 and 3, we could also put up here -1, any negative number or positive number, anything that can be written as a fraction is rational. If I want to remove some of those numbers, take a category out, let's take away all the decimals. Well, then I would be left with something like -2, -1, 0, 1, 2, and it would go on forever, and it would go on forever to negative infinity as well. So these numbers will go from negative infinity all the way to positive infinity. Integers are any number without a decimal. Any number with no decimal is an integer. So I can go negative numbers, positive numbers, 0, they're all included, but they have no decimals. Integers we can represent with a letter as well, and we're going to call it, the symbol is going to be Z. We're going to use the letter Z to represent integers. And even though it doesn't really make too much sense to use Z for integers, if we do a little research, we can find out that the German word for number is Zahlen. So I believe I'm spelling that right. Zahlen is the German word for number, and that's kind of where this comes from. Z, Z for integers to represent numbers. Now we're using it to specify specific numbers with no decimals, positive or negative, and 0 included. Now let's say I wanted to look at an integer, the number 1. Well, the number 1 is an integer. It's also rational, and it's also real. So rational is a subset of real, and integers is a subset of rational. So anytime we have an integer, it's also rational and real. Let's go one step further. Let's get rid of all the negatives and further specify, get a little more specific in our definition of numbers here. If we get rid of all the negatives, we're just starting with 0, 1, 2, 3, all the way up to infinity. Then we have what we call whole numbers. Now it makes a little more sense, a little better sense with the abbreviation as well for us Americans. We're into our language now. We're going to use W for whole numbers. So W is a whole number, and it's all numbers from 0 to infinity that have no decimals. No decimals. 0, 1, 2, 3, ... Now the ... I put 4 dots there. It's all right though. The ... indicates that we continue on in the same pattern. I add 1, I add 1, I add 1, I add 1. I keep adding 1 all the way forever. So from 0 to infinity, whole numbers, no negatives, no decimals. And I could further get a little more defined here. If I want to talk about natural or counting numbers, now if you think way back when you first learned how to count and first learned about mathematics, a natural or a counting number, what we teach to our babies, our young children, we start with 1 and we go from there. 2, 3, 1, 2. Having a little technical difficulty here, sorry. 3, 4, and on forever. So our natural or counting numbers start at 1 and they move on forever. And again, this one is a little nicer. It makes maybe a little more sense when we talk about our natural or our counting numbers. We're going to use the letter N. The letter N stands for natural or counting numbers. So now we should be able to classify any number, any real number, as by all of its subsets that it belongs to. All the subsets of real numbers that it belongs to. So if I told you, tell me about the number 5. And we could use and talk about each member of a set is an element. So 5 is an element. We can use this symbol, a backwards 3, can mean is an element of. 5 is an element of what? It's a natural number, right? Well, since 5 is a natural number, it has to be everything above it as well. It's a natural number, it's a whole number, it's an integer, it's a rational number, and it is also a real number. And we didn't talk about this, but the abbreviation for real numbers is R. Typically it's got a little squiggly, sometimes it's got a line through it, or you could just write it as R. Real numbers can be represented by the R. So what about another number? Let's choose something a little more difficult. What about 0? Well, 0, is it an element of natural numbers? No. Is it an element of whole numbers? Yes. 0 is an element of whole numbers, integers, rationals, and reals. And what about 3 halves? Negative 3 halves. What about negative 3 halves? Well, it's got 3 over 2, which simplifies to 1.5. So negative 1.5. It's not natural because natural has no negatives or decimals or zeros. It's not whole because there's no negatives or decimals. It's not an integer because there are no decimals with integers. It must be a rational because I can write it as a fraction. It is an element of rational and real. Let's talk about the number pi. Well, pi is an element of irrational numbers. It is non-terminating and it doesn't repeat. But we need to remember, folks, irrational numbers are still real numbers. So pi is an element of irrational and also the set of real numbers.